Yes, well, hello everybody. I hope you're doing well. Yes, so today we are going to talk about the cascaded neurosymbolic architecture of a DSP that we designed. And my name is Simba Fahad, student at Macquarie University, pursuing a Bachelor's of Science and Software Engineering. We are going to discuss why we did this system, the methodology and approach we use, data set descriptions that we went through, the results of the model itself, and perhaps I'll give you some references. You will hear me talking about the Bayesian Network. This is a causal inference engine that takes in spatial variate to make decisions. We shall talk about the cascaded inference. This is a chain, a cascade of these models that work hand in hand to come up with the final decision of scheduling. We shall talk about the GRU, the Gated Recurrent Unit, data processing of traffic and weather data. We'll talk about the Spatio-Temporal Synchronization Engine, the DST itself, the entire system. Then the support vector machine, which is the same as the policy enforcer. Just get ready for this long, insightful, and knowledgeable ride. We acknowledge the write-ups. One of them that was published in 2015 by Few. This research proved that the range shifts durations. Okay, it can shift the mode trace, and this related to the weather microservice of the DSTE, the system that you are building. Okay, but however, one of its weaknesses, it was static and rule-based. Okay, and the DSTE for itself was one of its objectives was to be data-driven scheduler. Okay, so we talk about the published in 2015 by Zoo. This system aided them to achieve an 9.7 cost savings, especially in short-range urban trips. But for the long trips, those outside urban areas, they were also big but not worth it. And this system had no the causal reasoning engine and no policy enforcer, so it could just say go or no without causal reasoning behind everything. Also, the work of 2024 by Chan, whereby these guys visualize flood stress speeds up. They use virtual reality. You put on a virtual reality and see whether it's raining where you're going or flooding, but it cannot automate the scheduling. With the interest of time, we shall talk about what drove us to this system. One of them being the scheduling that floods Macquarie access routes. And imagine the lecturer is traveling to the campus, but he's caught up in traffic due to these floods. Heavy traffic, say, a strong rainfall or bad weather, only for students to come to the campus, finding lecture being cancelled. So all the time wasted, the transport burnt and the fuel reposted is never regained, which is the sunk cost effect. Well, as we thought about these problems, we had to think about the computation problem that we might incur, and which is weather data processing and traffic data processing as well. Getting data from weather sensors and traffic sensors, which is kind of hectic. So we had to think about this, how computation this could be feasible. So, and also putting it all together with the university schedules and all those unsolicited events, we had to come up with research questions and objectives as well. And one of the most interesting questions was the key urban stressors that causes schedule failures and study commute losses at Macquarie University, of which we have traffic, weather, and also the events, just like we stated them earlier. The core objectives was to identify these key urban stressors, develop dynamic spatial synchronization engine, the DSTSE, using that proposed architecture, and also implementing those code audit mechanism. You give a reason why you're scheduling the lecture, putting it online or cancelling it, and also editing the policies of the institution itself using the Bayesian. This research, the entire research, when you build it all up, is to bring that decrease in lecture late starts or cancellations. You get the point. So those reduce on the sunk cost effect as well, especially at Macquarie University. Also supporting the policy support or data-driven governance, especially for bodies that may need traffic data or weather data, because these models, it's a microservice architecture, distributed architecture. So it's of course made in Uganda AI for researchers, and most importantly, the integration of Bitcoin transaction could set it apart, where people could also use this platform to transact with Bitcoin. So this is the proposed architecture of it. So it takes in weather data from the sensors and traffic as well, reprocessing them, feed them into the GRU, Bayesian Network, takes out the outputs of the GRUs, feeds them into the SVM, then the SVM applies the institution policies, which are of which its output is audited by the Bayesian network as well. If they are contradicting and the Bayesian has a high confidence, it overrides it right out, just like we would see it later in operation. Our the data visualization stated that distribution graphs for the atmospheric variables, and when we could see at this, we had the outliers. They were not above, they were below the minimum. Put this rate by interpolation, especially when they couldn't connect with weather. We took it to be human error when feeding in this data. These were atmospheric variables against the weather states, whether heavy, low, moderate, or very high. So the time series, you could see that these have a certain pattern over time. There's a spike here in rainfall, total rainfall, a spike also here. But when we try to visualize the total rainfall itself, we saw that it had outliers, but these are normal in rainfall data because rainfall sometimes spike. Okay, so those other outliers that didn't match or correspond to the exact data inputs, they were really interpolated and filled. So we can see that the minimum value of rainfall, total rainfall was 0, just like you could see here. When we visualize this, the total rainfall and count collected over time, we saw that the highest frequency was this over 80, and the overall correlation heat map shows that after engineering, making the rollings, the lags, and log transformations, the signs as well of hours, we saw that the regression variable and the classification variable with the category, rainfall category. But we saw that all these engineered features affected more on the regression part, so that it's for the continuous variable than the categorical one. Now we could just tell right away that in case of models, regressors would perform better than classifiers. With the traffic visualizations, we could see here the frequency of the count around 18 appeared most of the times, 20 cars or vehicles. The distribution, we could see that with very high, there were some outliers that needed to be put right in case they had no relationship that could validate their outlier nature. However, we use interpolation. I want to emphasize that. So we can see that the minimum log vehicle category was at around 5. Then the normal minimum was at around 18. The maximum was around this 25 or 30. So more with traffic pattern, you could see here that in the morning at around 5, there are people maybe just waking up going for work. Spikes very little, very hard. Flattens here in the morning, goes down a little bit when people have reached their workplaces. Flattens, normal traffic, then it hikes in the evening at around 3. This when maybe people are leaving their workplaces. So flattens, then falls deep late in the night. Yes, so we'll talk about these models. So we talk about the GRE, the random forest, and talk about the SVM and the Bayesian network. They are mathematical formulations. So let's start with the GRU. So the GRU has the reset and input gate. This the reset gate, the output gate, the sigmoid. So the sigmoid puts it to 1 or 0. If the output of this is all a 0, say that there's no reset here. If it's on, it says that we need to set something, okay? Forget something. Yeah, so these are the weighted arrays, and this is the bias of the model. So the same applies to this, the update gate, I mean. Then we also have the candidate state. Still, it has the bias, the weighted array. It's like the draft knowledge of the jury before the final state is produced. So this final state contains the blend of candidate state plus the previous old state together, just like you could see here. The hidden state, T-1, when it comes in with the input, get into this gate, candidate state is produced. Then they blend together all the outputs of the output of this, then to give you the output state and the new hidden state. So with the random forest itself, for the regressor part, because if this was our target, Y regression, whereby the R is the rainfall count, then also this the constant, the small constant, whereby we use the 1. So we had to first transform X because we are in the regression problem. We had to first standardize X, find now the new Y. However, remember that we said that this strip picks features randomly and also these points randomly. But when it's picking, it ensures that when it's splitting, it splits the points that into groups that give the minima, the mean square error, the minimum mean square error. Then with the classification part of it, instead we just have to coding those targets into integers, okay, for traffic. It caches the mode of the outputs of the trees, because in classification these are categoricals. X is defined as that the temporal features. This could be the input features. It could be the time, the hour, the rush hour, the what if it's always traffic. Then this is the road. Classifiers were used on traffic, regressors were used on weather. So the gain index ensures that each and every group split it's pure. Yeah, so it does this recursively until the gain index is big, or until when there is noise in the output. However, we use some structural constraints like the mean sample leaf, the mean sample splits, and the maximum depth. The maximum depth was the depth of each tree, then the mean sample splits, and also the mean sample depth to ensure that for each and every node to be split, there should be at least two points to validate to allow us to capture the mean. In structure, you could see that you could feed in the data, bootstrap it, randomly choose features, bootstrap sampling, feed them into the tree, splitting is done. Then each and every tree learns when each and every tree has learned, so we can now put in new data. Each of the tree processes the data, then we get the output. We aggregate. If it's regression problem, we find the mean. If it's a classification problem, we find the mode. So the SVM, just like we said, it has the input. The input, which is composed of the row stands for the traffic data. Omega holds the weather data, and this is for transport. So this one is converted into a column and row matrix. Then combination starts right out. But however, first standardize this X to get the new X, whereby we apply the RBA function that transforms it into a higher dimensional space. Okay, especially with data that is hard to separate. The Euclidean distance between the points that you put and our original X. When I talk of a point, I talk of a row, and I mean a row in your data. When we now go to the actual classification, that takes in this RVF. The bias of the model, this center equation times the same. Could be either a positive or a negative. We have now the convention objective equation for this. It has variables like the margin, W here, then the C. This C was too big. It's a penalty parameter in that we penalize the model highly for certain decisions. It's not following the policy. So this entirely, we first get X transpose it, standardize it, apply the RBF, then apply the function, then we can optimize, okay? When we go to the Bayesian network, the Bayesian network has these independent features of weather, traffic, delay, and the decision. It first takes in the variables that you have put in, those of weather and traffic, assigns them to the base rate function. Okay, yes, this function combines the weather component and the traffic component, but you can also ensure that it doesn't go above 1, the total probability. You can see here that now we can have a probability of decision given this evidence, weather and traffic, and the final decision, we could get the maximum of this, okay? The rate of decision given evidence. All right, so our results for the models were with weather data, we use the regression model, which got a 0.71, but is outperformed by the GRE, and traffic classifier here was also outperformed by the GRE with a rate of 97. The output of this, because you shall consider the GRE, then its output are fed into the Bayesian network. Bayesian network, we can see that when weather is bad and the traffic is heavy, it has online. When it's good, we prefer scheduled. We can see finally the SVM, the policy enforcer, that checks the performance of the SVM. It's one because this is the higher penalty. Okay, this C here, the C right here, it was big, meaning the penalty was big. So that's it for the result. So these are some of the extendable results when we try to test this model. You can see with your eyes that there's overrides. Overrides here, overrides here, and overrides in this row, and overrides in this row. Why did that happen? So this one happens when you're having weather bad and on a Bayesian network auditor. So the SVM said that we would be scheduled, but this was the BN auditor said that to be online, and this person is a 65. So there was an automatic override, okay, with reasons as well. Also the same applies here. Scheduled and online the same. Scheduled and online also the same. So these are override scenarios, but however, they also say that neither the SVM nor the BN should be out of the equation because they work hand in hand to bring up something better. All right, so we go to the model compressions. So the model compression pipeline, we had the original GRU because they compress only the GRUs for the weather. Okay, the GRUs for the weather and traffic because they were kind of big. They didn't compress the SVM and the Bayesian because the SVM was too small, okay? For the Bayesian, you cannot move nodes because you may break the system. All right, so here we shall have the pipeline having the original GRU, the layer pruning, a weight pruning, then we apply noise distillation and quantization last. So, pruning, you reduce either the weights or the nodes in the model. Then we train distilling. How does distillation occur? In this lesson, when the parent outputs data and the student outputs data, it's a the student to learn from these patterns. Okay, yeah, so the student learns from these patterns put up by the parent, so that it updates its parameters. You get the point. So this session occurs here, but there's also a certain hyperparameter that we use that we train it is named as temperature because it needs to expose some of the relation of its outputs to the student for learning. So we finally apply the decision techniques and finally the condition techniques whereby we could have a floating point matrix which is converted into an int8 output compressed model, then plus the mapper. The mapper shows the metadata of each and every transform the array. So compression results show that the model with the traffic shows that it was 155 point schedule, but now it's 18, closely an 88% storage reduction. So the same applies to the weather, model compression, the number of parameters, and the deployment pipeline. We could have Dockerizing the traffic microservice. We did that. Dockerizing weather microservice. We also made the Dockerized decision engine a microservice. Also Dockerized the lectures user interface. On the right, the certain scenario where the Bayesian overlap to the SVM due to its high confidence. Yeah. So, well, the limitations for this research is that it's designed for Macquarie University context currently. However, we have expert APIs for researchers and developers. And so we also have expert trials for the DNA SVM due to sparse data at the campus. And we also had a gap in rainfall data because it's spaced from 8 to 16. So, well, the feature works and foundation, and conclusion is embedding the LoRaWAN into our nodes so that they can communicate even offline, having developing umbrella application development for public facing and for especially entities like student researchers and other entities. So also adding Bitcoin payment system integration. And also remember that Macquarie University DSSE represents a paradigm shift from reactive administrative interventions to a predictive data driven connection supporting Bitcoin. These are the references. You can see them, but also we have these other references for the model compression specifically if you wanted them. Yeah, so we activate Mr. Galuwango for his support, feedback, and guidance throughout this entire journey. Alison.com, thank you for the content that you post. It was one of the major questions that pushed us even further to take up with machine learning project. And lastly, Macquarie University Berkshire for offering us the data. Yes, without wasting even more time. Thank you. Have a good one. Be updating you on what's next.